Quantitative analysis. What is quantitative analysis? Quantitative analysis is the measuring of the quantity of a substance. There are two terms that we use to talk about the quantity of substances in a chemical reaction. The first is limiting reagent. This is the reactant that is completely consumed during a chemical reaction. When it's consumed, the reaction will stop. The excess reagent is the opposite. It's the reactant that is present in more than the required amount to complete the reaction. So how do you determine the excess or limiting reactants? First of all, you write a balanced equation representing the reaction. Write the chemical formula for each reactant and product, including the state of matter, solid, liquid, or gas, for each one. Try balancing any atom that is not polyatomic ion and is not oxygen or hydrogen. If possible, balance polyatomic ions as a group. Balance the remaining atoms and molecules, taking into account the oxygen and hydrogen atoms and water. Leave until last any element such as H2 or O2. Check the final reaction equation to ensure that there is the same number of each type of atom before and after the reaction. So here's an example of balancing a chemical equation. In the original equation, we have Na3PO4 in an aqueous state plus CaCl2 in an aqueous state to produce Ca3PO4 in a solid state and NaCl in an aqueous state. Now we need to balance this equation, so let's review that. First of all, we'll write the equation and then we'll try and balance the sodium. So we now have 6 sodium on the left, so we will need 6 sodium on the right. Now that gives us 6 chlorine on the right, so we must have 3 on the left times 2, 6 to balance. And our answer, now that it's balanced, is what we've determined, so we are correct. Now, here's another term, the mole ratio. We all know that the mole is a measure of molecules or atoms or whatever we're talking about. And we will use the mole ratio in our balancing of chemical equations. To do that, consider the synthesis reaction that occurs when zinc metal, Zn, is heated with sulfur, S8. And yes, we're balanced. Predict the mass of ZnS that would be produced from 1 gram of zinc. Steps. Number 1, we're going to convert the mass of 1 gram of zinc into the amount of moles. We're then going to use the mole ratio given in the equation and predict the amount in moles of the product that is given by the mole ratio. Then we're going to convert the predicted amount into moles of ZnS into mass. So, first of all, we write the balanced equation. We make sure that everything is correct. And then we write the mass of Zn, which is 1.0 grams under the Zn. And then we write underneath, converting it, we write the molar mass, which we get from our periodic table for each. Then in step 3, we're going to convert the mass of 1 gram into the amount of moles by using N, which represents the amount or the number, 100 grams, or sorry, 1.00 grams times 1 mole, divide by 65.38, and then we do the math and we get 0.0153 mole. Now, we fill that in to our data. And now we're going to use the mole ratio given in the equation. The mole ratio prescribes 8 mole of ZnS for each 8 mole of zinc, and it's a 1-to-1 ratio. So therefore, the amount of ZnS is also 0.153 mole. Then we can enter this data provided underneath the equation. Now, once we've done that, we do the math. Since we want to know the mass of ZnS produced, and we know that there are 0.0153 mole produced, we convert the mass. So the M, which represents the mass, is 0.0153 mole times 97.4 grams times 1 mole, and we get 1.49 grams. So what is our conclusion? The mass of zinc sulfide produced by the reaction of 1 gram of zinc with sulfur is 1.49 grams. The next thing we want to look at is how to calculate the limiting and excess reagents. When reactants in a chemical reaction are mixed together, the quantities that react are determined by the mole ratios in a balanced equation for the reaction. It is important to know the minimum quantities of each reactant needed for a desired quantity of product. In industrial processes and laboratory procedures, they are designed so that one of the reactants is used as the limiting reagent and the other reactant are used in slight excess. Using gravimetric stoichiometry, we can now calculate the exact quantities of reactants needed for a reaction. It is also possible, therefore, to calculate the quantities needed for a reactant to be present in excess. Let's take a look. As a general guideline, an excess of 10% should be sufficient to ensure that the limiting reagent is completely consumed. So here's an example. Let's look at the reaction of methane, CH4 as a gas, burning insufficient oxygen to produce carbon dioxide and water according to this given formula. If we are burning 2.0 mole of CH4 as a gas, how much O2 would be needed? The mole ratio in the balanced equation tells us that the ratio is 1 to 2. Therefore, 2 mole of CH4 would require 2.0 mole times 2 equal 4 mole of O2. To provide excess oxygen, we would add 10% excess, which is 0.4 mole, and so provide 4.4 mole of oxygen. Since we cannot directly measure moles, we can convert the amount in moles into a mass. The molar mass of O2 is 32 grams per mole. The mass of 4.4 mole of O2 then would equal 4.4 times 32.0 gram per mole to equal 140 grams of O2. Now let's look at a sample problem. In an experiment to test the stoichiometric method, 2.0 grams of copper 2 sulfate solution is reacted with an excess of sodium hydroxide in aqueous solution. What mass of solid sodium hydroxide is reasonable to use? Now we remember the formula, molar mass, capital M, is equal to mass little m divided by the amount N in moles. So we have CuSO4 plus NaOH to get NaOH2 plus N2SO4. We have 2.0 grams of CuSO4 and we have 159.6 grams per mole with 40 grams per mole of NaOH. So N, which is the amount, is 2.0 gram times 1 mole over 159.61 grams per mole, and we get 0.0125 mole. Then we do the same process for NaOH, and we get 0.0250 mole. So then we're going to find the mass of the NaOH, and we know that we have 0.025 mole. We know it is 40 grams per mole from its periodic table calculations. Divide by 1 mole, and that's equal to 1 gram. So the excess, if we add our 10%, is 1.00 gram plus 10% of 1.00 gram is 1.10. So if we were doing this experiment, a reasonable amount to use would be 1.10 grams of NaOH. How to determine the limiting reactant? Number 1, write a balanced equation for the reaction. Number 2, select one of the reactants and calculate the amount in moles available. Number 3, use mole ratios in the balanced equation to calculate the amount in moles needed of the other reactants. Number 4, calculate the available amount in moles of the other reactants. If the available amount of a reactant is more than sufficient, it is in excess. If the available amount is insufficient, it is limiting. Here's an example. In the combustion of magnesium metal in oxygen gas, 6.73 grams of magnesium and 8.15 grams of oxygen gas are available for the reaction. You are asked to identify the limiting reagent in this equation. 2 magnesium plus oxygen gives 2 MgO. Number 1, Determine the mass of oxygen gas needed to react with 6.73 grams of magnesium. So we find the molar or the number of moles of magnesium, 6.73 grams times 1 mole divided by 24.3, and we get 0.277 mole. So our mole ratio then is 2 to 1. So N of O2, 0.277 mole of Mg times 1 mole O2 divided by 2 mole of Mg. So that works out to be 0.138. So N of O2 is 8.15 grams times 1 mole of O2 divided by 32.0 grams is 0.255 mole. So we find that we have more oxygen available than is needed, so oxygen is in excess. The same conclusion is reached if we had done it the other way, by using the mass of magnesium oxide. So the limiting reagent is magnesium. And we've got the calculations worked out here for you. So NMG is 0.277. The mole ratio is 2 to 2. So NMGO is NMGS, 0.277 mole. The mass of NGO is 0.277 mole times 40.3 grams divided by 1 mole is 11.2. It's handy to keep these formula available when doing this assignment.